So my name is Marco van Beek. I'm the technical director for KLAREN International. And today I will be speaking about the implementation of the self-cleaning technology in evaporators. In this, I would also like to focus a bit on some important design criteria or considerations that you can make when looking upon the integration of our technology within evaporators, being either multi-effect evaporators or being MVR evaporators. To start with, who are we? KLAREN International is a Dutch engineering and technology company. We are based on a technology which is around already for quite a long time, but our company itself is relatively young, and since a couple of years we have become part of the Taproge group. Taproge is a German company that focuses on cleaning of heat exchangers, condensers, using a system with sponge balls. So sponge balls are circulated through the tubes, and in fact by the movement of the balls, the heat exchanger tubes are cleaned, and thereby increasing the efficiency. The main application is within the condensers of bigger power stations, where the technology really has a huge benefit and can save a lot of energy. So we became part of this group, so we're now backed with a larger organization. But as KLAREN International, we are an independent firm, and as said, we are based in the Netherlands. We have a team of process and mechanical engineers. That's our base team, because we engineer the systems, but we do not manufacture them. For manufacturing, we will always collaborate with a manufacturing company that can manufacture the heat exchanger components, which are always pressure equipment, so a lot of legislation norms, and you need good craftsmanship to get a good product. So we are not involved in manufacturing, but we will coordinate, and at the end we will also commission the units. Outside our company, we work together with a network of specialists. To give you an example, if we need CFD calculations, which regularly we do need, we work together with specialists that provide those to us. So this is a kind of a network approach. Since 2 years, we're not only based in the Netherlands, but we also have a base in India, where our engineers are situated within the Taproge organization, which has its base in Mumbai. And we're very happy with that. To start with, what is in fact the topic of today? The topic of today is fouling, our technology to solve fouling, and fouling in evaporators, and how to integrate our technology in these evaporators. What is then the problem that we want to solve? Well, in fact, you can see that on these pictures. In these pictures, you see the fouling as was occurring on the evaporator tubes of a forced circulation evaporator, which was part of a multi-effect evaporator that treated the wastewater coming from a dye-stuff producer in India. And as you can see, that this fouling was really substantial. So thick layers developed in the tubes, sometimes even complete tubes were clogged. But also on the tube sheet, you can see a lot of dirt agglomerating, which even blocks the tubes. Overall, this led to a very dramatic decrease of the evaporation capacity. So this as an example, but in general, fouling will always, for evaporators, reduce the evaporation capacity. But it also means that if you design an evaporator and you have to think about which fouling or which heat transfer coefficient to use, that you need to incorporate a fouling factor that compensates for the loss in heat transfer. And when doing so, of course, the area that you require for an evaporator, a heat exchanger bundle, will increase. So oversizing of equipment. But fouling will also mean that every now and then, and for some plants it can even be once every 2 weeks, you need to open the system to clean it. And that, of course, you can do it with chemical cleaning, so you don't need to open it, but you have to flush the whole unit with a chemical solution. which can dissolve the layer, or you have to open it and you have to clean the evaporator with mechanical means. Both options can work. It depends a bit on what type of fouling you have. For some foulings, chemical cleaning is not a solution because the layer itself is so hard and it will not dissolve, like for example with calcium sulfate. So then you need to open it, and that can easily take then 3, 4, 5 days, depending on the size of the system, before it's cleaned, and then it has to be reassembled again using new fittings, new gaskets. Yeah, so all kinds of additional maintenance costs, which add on the total cost of fouling. So all in all, there's quite a lot of money involved, a cost involved when you have fouling issues. And in fact, operators, they want to run the evaporator and they don't want continuously to clean it. They want to make maximum use of the equipment that they have purchased. Our technology is a solution to overcome this fouling. Our technology provides a continuous online and inline cleaning mechanism within the heat exchanger tubes. Since we talk about evaporators, we in this presentation and also for our technology, we focus on the forced circulation evaporator, which is a widely used evaporator and which is also the preferred choice if you already expect fouling. But in this technology, or in this forced circulation evaporator, we can integrate our technology in this vertical tube bundle, because we need the vertical orientation to get to a proper fluidization. Because in fact, fluidization, the use of cleaning particles in the tubes of the heat exchanger, is the core of our technology. We feed those particles, as you also can see in this animation, to the inlet of the heat exchanger. And in this inlet channel, which is in fact the bottom circle, which you can see here, in this inlet channel, we distribute the particles over all the tubes. And these particles are taken upward with, oh, sorry. Sorry for this. Let's see how I can end this. So we fluidize those particles inside the tubes, and if you would zoom into such a tube, you would see that these particles will move in a chaotic manner. They will, let's say, impact each other, and they will also impact the tube wall. And by these very light impacts, in fact, we create the scoring mechanism that continuously gives this cleaning effect on the tube wall. After that, the particles have been transported through the tube. We use a separator, which you can see here at the right top. We use a separator to separate the particles from the liquid. And the particles are then recirculated via a downcomer. So this tube which goes downwards, which is filled with particles, back to the inlet. The liquid that is after the heat exchanger will then pass through the next step in the process, which for an evaporator will be the vapor liquid separator. What it's also good to mention is that to get the particles moving, we use a small side stream, which you can see here at the bottom. We use a small side stream which acts as a control flow, by which we can control the amount of particles that is flushed into the inlet channel. So this is what we call the control flow. So all in all, the fluidization, the chaotic movement of the particles, that is the core of our technology. What is good to mention that the particles have three main effects. First of all, they give an impact with the tube wall, and by this impact, and the developing fouling layer is removed. So that is one. The second thing is that these particles, they improve heat transfer. So by their chaotic motion, they also pass the boundary layer at the tube wall, effectively mixing it and making heat transfer better. But then it's good to mention one other element, and that is that we run our heat exchangers at a lower tube velocity than you would normally have in a conventional shell and tube heat exchanger. Because if we look at state-of-the-art designs, then you would see that you would apply tube velocities of between, well, at least above 2 meters per second for a shell and tube heat exchanger. But in our technology, that would not work because that would lead to too aggressive particle motion. So we use velocities which are around 0.6, 0.7, sometimes up to 0.8 meters per second. But then, of course, with 0.8 meters per second, you would have a reduced heat transfer coefficient compared to 2 meters per second. But by the action of the particles, we get to comparable heat transfer coefficients, which, of course, will be constant over time, which is a big benefit. The last thing to mention, and that is also relevant for evaporators, is that the particles will also create an internal shear in the liquid. And this shear will, for liquids that in fact have a behavior which you can call non-Newtonian, will reduce the viscosity. And by reducing the viscosity, the heat transfer coefficient is improved. That is, of course, very, very beneficial for the design of the heat exchanger. If you look at evaporators, sometimes you can concentrate the liquids to high concentrations, like for example, you also have that with vinasse in the sugar industry, but then viscosities can become really high. You will not find that really with wastewaters that contain a lot of salts, but for wastewaters that contain a lot of organics but long chains, definitely a strong concentration could lead to high viscosities, and then the fluidized bed could reduce this viscosity by the action of shear. So this is in fact a very important slide in my presentation of this afternoon in the webinar, because it really shows the core of our technology. Let me go on to the next slide. If you then look at examples of our system, then it's not only that you can use the self-cleaning system with a fluidized bed for evaporators, but you can use it for all kinds of heat exchangers. And in this slide with 4 examples, you see 2 of them which are not related to evaporation, but are related to different applications. The right top is the production of a proprietary chemical. In the USA, this system is in use already for a long time, more than 25 years in operation, having many operating hours. Before they installed the self-cleaning system, they had to clean it more than once per week. And after installing the system, well, in fact, the number of cleanings went to 0. In this application, the fouling was because of a waxy deposit, so a sticky deposit that created strong layers, and in fact, what I always said led to these cleanings. But after installing, the performance was really to the satisfaction of the customer. The bottom right is the heating of a zinc phosphate solution. This application is in an industry where they coat metal parts. They coat metal parts with a zinc phosphate layer because this gives protection against corrosion. Metal parts are put in a bath where this zinc phosphate solution is, and that will then deposit on the metal surface. But of course, if you put fresh cold parts in this bath, it will cool down, and to keep it up to temperature, there is a continuously heater. And this heater, well, it's coated by the same process, so that's in fact the core of the fouling issue. So we have installed this self-cleaning system, and it was in continuous operation with very good performance. So another example of our system. On the left side of this slide, you see two examples that we will discuss a bit more in detail in this webinar. Both are for evaporators. One is for a 4-circulation evaporator, part of a multi-effect evaporator, 4-stage. And the bottom one is a single effect evaporator in Japan, already now in operation for many years. But as said, I will come back on both in the course of this webinar. So, the fluidized bed technology as self-cleaning online and inline cleaning system can be applied in many applications, and that can go as far as the removal of ice from tube walls. Then going a bit more in detail into the integration of an evaporator, the implementation of the self-cleaning technology in evaporators. I will show two cases. One is a new build case and the other one is a revamp case. So they have their own characteristic, their own dynamics, because of course in a new build you can design from scratch, you can make all the choices you want, but in a revamp you have a lot of limitations. So the first one is an evaporator used in Japan to treat wastewater coming from a distillery. And in this distillery, they made the alcoholic liquor called soju. And after this distillation, wastewater is left that contains organics and salts. And already up front, they said, well, fouling will be substantial. So let's see if we can apply the self-cleaning technology. And they did already from new build on. It was chosen to use a single effect evaporator with TVR. So that's not the most beneficial if you look in terms of steam economy, but they chose to only have one effect. If you have one effect, then to improve steam economy, the only thing you can do is apply a TVR, which they did. This TVR also created a light vacuum in the vapor liquid separator. The fleet flow to this unit was around 2 cube per hour, so it's not a very huge installation. As you can also see, the heat transfer area was only 85 square meters. And in this application, we run with 2 millimeter metal wire particles. And that's maybe also good to say at this moment. For the self-cleaning technology, the fluidized bed technology, we can apply different materials. One option is to use ceramic beads. Ceramic beads have the benefit that they are lighter, and that means that you need less pumping power, but also the removal mechanism is less aggressive. The other option that you have is to use metal wire particles, or what we also sometimes call cut metal wire, because in fact it's made by cutting a metal wire into small cylinders, and those cylinders then will get a surface finish to take off the sharp edges. So in this case, a metal wire of 2 mm. It was quite a viscous solution. That's also what you see in the heat transfer coefficient, because that was only 930 watt per square meter Kelvin. If you have a liquid wastewater and aqueous wastewater, which has solid concentrations between 10–15%, then we easily could get to 1500 watt per square meter Kelvin, which you also have seen real life. Yeah, well, the system was built, installed, and we can now say that it has been in operation for more than 23, or let's say around 23 years. And the experience has shown that only once per 5 years they open the unit, just as a regular maintenance interval, where they inspect the parts and where they just check everything. And when required, parts are replaced, but let's say that's rather limited. And the tube bundle, and that's really an important thing that we can prove with this slide, is a main question we always get is, how is it with erosion of the tubes? Will the tubes erode at the end, and will that lead to leakages? But we can say that the action of the fluidized bed will not influence the tube wall thickness. And that's also proven in this application, because they replaced the tube bundle after 15 years. but that was just because of preventive maintenance. There was no real reason behind it. A real reason could be, for example, that they had leakages, but that was not the case. But they just wanted to be sure, and by let's say the decision, they decided to change the bundle to be on the safe side. They run with a concentration factor of around 3. In fact, they could go higher, but for them at this moment it's good enough. But of course, there is a benefit if you look at evaporators. I mean, what is the use of an evaporator? You want to recover the water from a waste stream. So if you can go to higher concentrations, which we can, of course, your water recovery will be higher. So this is, in fact, the new build case. Then going to the second case, and this is the revamp case. What is our approach behind a revamp? Well, maybe first to start with, why would you consider a revamp? Well, I think that's rather logic. I mean, suppose you already have a multi-effect evaporator plant, and you know that in one of the effects you have substantial fouling issues. And of course, yeah, the best would be that we can change the existing system and not offer a complete new one, because changing it will, in most cases, will be a lot more cheaper than building something new. So the advantage is you simply have a lower capital investment, since we will reuse some of the parts. And of course, what is the most expensive part is of course the tube bundle itself. So if we look at the revamp, we will always look at to reuse, so that's the starting point, the available heat exchanger, the available bundle. The next thing we will then do when we will assess such a situation is that we look at the performance, so the process perspective. Why? Because of course we want that the capacity of the unit will not change, that it can still evaporate the same amount of water or more, but definitely not less. So we analyze the existing installation, the existing performance as it is, as in the as-is case, and then we will make our calculations to show or to prove that we, with our technology, can get the same heat duty of the heat exchanger or even improve it. So that's the thermal evaluation that we will make. The second thing we do is that we look at the plant layout. Why? Because I earlier described how our system works, but in this functioning, we need some different components, additional components. For example, we need a particle separator, at number 5 on the picture on the right. We need a downcomer. That's mostly not so complicated, but we also need to install an inlet channel, number 7 in the picture. And for this inlet channel, we need some space underneath the tube bundle. For the particle separator, we need some space between the heat exchanger bundle, number 1, and the vapor liquid separator, number 2. So when we assess a revamp case, we always have to look, can our particle separator fit in between the other components, and is there space enough in the plant? So that's the mechanical perspective. Based on this everything, we will at the end draw up a feasibility report in which we discuss the several topics and which gives, let's say, the input to the client to see, is it possible? Yes, or are there things that we need to still change? For example, that could be the pump. Preferentially, we will reuse the pump, but that's not always possible. And based on that, we then can, or the client will decide if he moves on for a project or makes a different decision. But we will always take the professional approach in providing a good feasibility assessment. Well, we did this for the first project we have done in India. And this was the first effect of a 4-effect multi-effect evaporator plant. Already mentioned before, the pictures in the beginning were from this plant. It was cleaned every 4 weeks. Yeah, I would say almost dramatic fouling. The fouling came because the effluent contained calcium sulfate with some other salts in combination with organics, and this led to very hard fouling. and a very thick layer with a strong effect on evaporation capacity, but you will see that in the next slides. So we revamped this to the self-cleaning configuration, and revamp in this case was, I would almost say, rather easy. Why was it easy? Well, we're a bit lucky that the heat exchanger, the existing one, was a 3-pass arrangement of the tube bundle. And why is it beneficial? Well, as I said earlier, we use lower tube velocities. And when you use lower tube velocities, it effectively means that your flow would reduce. And when you then want to get the same evaporation capacity, you need a bigger delta T of over the tube. But you also need, let's say, less length in the tube. So effectively what we did is we converted the 3-pass into a single-pass arrangement. So then you get 3 times the number of tubes for the flow to go upwards. We reduced the velocity with a factor of 3. So effectively, we got the same flow, the same delta T over the tubes, and in fact had the most ideal configuration for a revamp. And since our heat transfer coefficient improved compared to the original design, in fact, the evaporation capacity has gone up for this total plant. So even the revamp has brought additional capacity. It was a substantial installation in terms of size, because we talk about 373 tubes, shell diameter of higher than a meter. The tube bundle was 6 meters long, which is quite a standard size. And in this case, we also have applied stainless steel cut metal wire particles of 1.9 mm. Okay, so this was done. This was the revamp. You can also see the picture of the components in the 3D CAD drawing, where you see the downcomer, in fact, on the downcomer, the particle separator in the middle, the downcomer going downwards here with 2 inlet channels into the inlet channel where we distribute the particles, and then the particles move upward through the tube. So what was the result of this revamp, which of course is the most crucial from the customer perspective, but also for us, because at the end, KLAREN is only interested in doing good projects. We're not interested in delivering a system and then a client just can't see, but we want to be involved in the plant performance, just to assist. Because when a multi-effect evaporator, it can also be that fouling will not occur in the first effect or the last effect, but in an effect which is not equipped with self-cleaning. But still, then there are things that we can do to improve the situation. In this figure, what you see with the blue triangles is the evaporation capacity as it was before the revamp, before the retrofit. And you can see that within 300 hours, the evaporation capacity dropped with 50%. So within 10 to 12 days, this evaporation capacity really went down dramatically. After the revamp, which you can see in the red triangles, the evaporation capacity of the plant has remained constant. And that, of course, is exactly what the intention was behind the project. But since it's a multi-effect evaporator, you always have to await what are the other effects are doing. You see some fluctuations in the points. That's because the data is raw data from the plant, so we did not manipulate it in any way. And because it's daily averages, there is some fluctuation in the recordings. I see some questions coming in, but I would definitely look at them, or I will answer them at the end. From previous webinars, we know that has given the best, let's say, presentation, at least from our perspective. Yeah, so a very positive result, and in fact, we have just completed also an inspection of this unit after 7,000 operating hours, which would normally fit within 1 year, but it's not run continuously. So we did it at almost 2 years of operation, and the plant condition was really, really good. Okay, so just shown you two applications, one new build, one revamp of the integration of the self-cleaning technology in evaporators. Maybe now some more specific words about first the multi-effect evaporator plant, and second an evaporator plant using MVR. But I will start with multi-effect evaporators. Well, I think most people will know you use multi-effect evaporators to increase steam efficiency because you put a lot of energy into the conversion of water from liquid to gas, to vapor, and of course energy use is always money. So you want to make maximum use of this energy, and you can do that by using the vapor generated in one effect to be used as the heating medium in the next effect. And you can do that by having a cascade of pressures, and then you call it a multi-effect evaporator plant. Academically, you could use many effects, but what you see in practice is that 4 to 5 effects is about the maximum. The vapor coming from the last effect is then condensed in a condenser, and that's in fact where you let's say it also kill the energy. To further boost steam economy, you could use a TVR in the first effect, or from the first and the second effect, and then you take some of the vapor. You use a thermal compressor to upgrade, or to upgrade this vapor using fresh steam, and the net effect of using a TVR is the same as adding an additional stage in your multi-effect evaporator plant. So you see it quite a lot. In the schematic picture, which is forward feed system, so the feed enters at the first effect and leaves at the last effect. In this picture, you see that all stages schematically are equipped with the self-cleaning technology. But this is definitely not always possible because that can become too costly, and then simply the business case will not work. So in many cases, we have the discussion with clients to say, okay, which effect are we going to equip with self-cleaning? We then base that on the experience that a customer has, but also on the combination between temperature and concentration. So if you have a forward feed, the maximum concentration is in the last effect. But if you take a backward feed, you can combine the highest temperature with the highest concentration. So that's definitely an option. But this is an important design consideration. Which effect are we going to equip with self-cleaning? This was the multi-effect evaporator plant. Then another possibility is to combine self-cleaning technology with the MVR principle. And what is MVR? MVR stands for mechanical vapor recompression, sometimes also called mechanical vapor compression. That's a bit of a synonym. But the core principle is that you take the vapor that you generate from the evaporation, you take this vapor and you upgrade it in terms of pressure and temperature by a compressor. And by the compressor, as I already said, that the temperature or the pressure is changed, and the outlet discharge pressure is higher than the inlet pressure. And because of this, the temperature is also higher. And that's where you create the driving force to use this vapor on the shell side of the heat exchanger that you use for evaporation. So you use all the vapor that you generate to condense again. And effectively, you recirculate this energy. What you do need to do is, of course, upgrade this vapor in pressure, and you need electrical energy to do this. So the energy input to this installation, the main energy input, is by electricity that goes into the compressor. But since you use all the vapor from the first effect, which is the only effect, and condense it, there's only effect required. And that has as a positive implication that there's no discussion anymore which effect to equip with self-cleaning, because there is only one, and this one will be the one that you equip with self-cleaning technology. So that's very beneficial if you look from that perspective. But there's also a second perspective, which I don't want to discuss in too much detail today, because it's part also it's also part of a separate webinar on MVR units. But if you look at the energy use, an MVR has a much better energy than a multi-effect evaporator plant, even if it's a 4 effect with TVR, as you can see in this table. Just using engineering equations, you can calculate how much energy you need to evaporate 1 kg of water in an ME. You would need around 0.3 kg of steam, but you need to drive all the motors of the recirculation pumps in the various effects. So that's the energy, the electrical energy use that you have. And if you calculate this the same for an MVR, so you can calculate how much pressure you need to increase the vapor. From this, with the equations for a compressor, you can calculate how much electrical energy is required. So you will get to an energy use of 0.06 kilowatt-hour per kg evaporated. So that's even not that much higher than the electrical energy that you already have in an ME. But if you then convert both of those energy inputs into principal or primary energy, so being coal, and this is, for example, in India quite common. So you can use then the coal in a boiler to generate steam, and for the multi-effect evaporator, or you use the boiler or the coal in a power plant to generate electricity. And using the known electrical power plant efficiencies or a boiler plant efficiency, you can calculate how much coal you need to evaporate 1 cube of water. And then you see that the MVR only uses almost 60% of the energy of an ME. So that's really a lot of energy saving that you can accomplish with an MVR. Still, you talk about rotating equipment, and many people fear rotating equipment a bit in that sense. So MVR still has to deserve, especially in India, its place in the market. But that's also, in my opinion, because some systems are not properly designed. But yeah, let's say that's too much detail for this presentation of today. But you have to really be careful that the energy balance in an MVR is okay. I will say something about that later. So based on this, some important selection criteria, design parameters for both ME and MVR. Well, ME is a straightforward system, but you need to look at steam economy, and you can optimize this. And it's important to carefully select which stage to equip with the self-cleaning technology, where you can, let's say, think about forward versus backward feed. If you look at MVR, well, it involves rotating equipment and care, as already said, so that's important to consider. But it's also important to look at how you balance heat transfer area and compressor ratio. Because compressor ratio, you can increase that, but you use more electrical energy, but you get more driving force, and you can use a smaller heat exchanger. Or you can say, I lower my compressor ratio, I lose less electrical energy, but I need a bigger heat exchanger. So that's the CAPEX versus OPEX question. And the last point, and let me just say some words about this, is that an MVR requires a positive energy balance, meaning that you need the energy in the condensing vapor to be used for evaporation. But if you lose energy, for example, because insulation of your plant is not good, or because your preheater is not functioning correctly, you lose too much energy and you get a cascade that goes down, because you can evaporate less. You have your blower, it condenses in the heat exchanger. You lose again too much to heat loss and to preheat, and again you can evaporate less, so that circle only goes down. So you require a positive energy balance. If you want to know more about that, please also raise the question, and we can later have communication on this. One thing, just also as a small bit of advertising, is that together with our partner in India, Sachi, we have developed a standard packaged MVR evaporator that applies to self-cleaning, but we can supply this in all countries. It's a standardized unit using a roots blower as MVR. Of course, our self-cleaning technology is integrated. Next to the skid, we also have one container that contains some tanks and pumps. And we standardize on 2 evaporation capacities, being the 500 kg per hour and the 1000 kg per hour. The only required utilities will be electricity and fresh water. Then, in the last part of this webinar, some words about what is the business case of self-cleaning evaporator. And the most important, what we think, is the evaporation capacity itself. Because if you buy a unit and you want the unit to work for 2 cube per hour of feed, and at the end you can only do 1 cube per hour, of course you have paid for something which you don't get. And effectively that happens when you have a plant with fouling, because that evaporation capacity starts at 100, and within 28 days in this example, and that can change per client, it goes down until 50%, and that repeats itself after the plant has been cleaned. If you take the mathematical average of this, then you end up that this plant only does 60% of design. On the other hand, if you have a plant with self-cleaning, of course that's what we aim for, is it remains at 100% of design. So this is a huge difference in capacity, which already would mean that the self-cleaning version can already be 1.5 times as high and still have the same capex cost per cube. But on the other hand, there are still some other benefits as well, because with self-cleaning, and I will show you that in a while, you can have an optimized design, meaning that you need less area. You can reduce the pumping power. As said, you have the constant capacity, and there's no cleaning required, so no cleaning cost and also no downtime for cleaning. Optimized design, what do I mean with that? Well, this is just an example, and what we later will do is that we will in our website also provide a calculator to in fact calculate simple MVR units. So you start with saying, by the way, I should say that in this slide the aim is to show you the difference between how the design would look like for a self-cleaning arrangement versus a conventional arrangement, being the heat exchanger. So let's start with the feed concentration. So that in this example it's 2 cube per hour. We want to concentrate from 5 to 30%. Then you already can calculate that your evaporation rate will be around 1720 kg per hour. In this example, I've assumed that we evaporate at the atmospheric conditions, so at 100 degrees centigrade, and that the vapor that we have, either from fresh steam or from fresh steam combined with a TPR, is 117 degrees. So you see already, this is a difference of 17. But you have to consider boiling point elevation, so that will reduce the driving force. You can then use this, but it will be the same for the self-cleaning heat exchanger as for the conventional heat exchanger. You can use this to calculate how much area do I need, how big does the heat exchanger need to be. So for the self-cleaning, we always will have single pass, so I've assumed a 6-meter bundle. The heat transfer coefficient is 1300 watt per square meter Kelvin, and then I can calculate, even with the numbers on this slide, you can already calculate that the heat transfer area is around 90 square meter. If I do the same for conventional, then their heat exchange coefficient is higher in the clean case, but you have to assume the fouling factor, because that will happen over time. If you don't assume it, the capacity will even go down even faster. So I've just taken a normal fouling factor, and then you end up with 960 watt per square meter Kelvin. But that's already that's only 74% of our heat transfer coefficient. That directly reverts back to how much heat transfer area that you need. So we would only need 90 square meter, which is investment in terms of euros, dollars, or rupees, versus the conventional, which would need 118 square meters. And if you look in terms of flow, because it's a forced circulation evaporator, the flow is high, but the flow in our case would be smaller than the one for conventional, and also the head would be smaller because we only have single pass, of course, with the fluidized bed, But if you have 3 pass and in total your bundle or your length of the tube is 80 meters, you see that you get a substantial pressure drop of 7.8 meters. So that converts back to pumping power. So the pumping power in our case would be around 8 kilowatt versus the pumping power conventional of 15 kilowatt. So you see that there's also a benefit in going for self cleaning. So ending with some conclusions. Yeah, well, evaporators with self-cleaning offer operation with constant capacity, no need for cleaning, as said. So yeah, clear that of course this is desirable. Design is optimized in terms of heat transfer area and pumping power. And you can integrate it in both multi-effect evaporator plants as in MVR plants. Both is possible. And in fact, we do not really have a preference. Of course, looking from the world perspective in sustainability, using less energy is preferred. But local circumstances can really make that you make a different decision. And that's, of course, really, let's say, understandable. And to end, we do not always need to only build a new plant. We can revamp or retrofit existing plants, but it requires a professional approach, which we will do in a feasibility review. Well, the last thing I want to announce, so after these conclusions, is that we have prepared a calculator which you can use to calculate an MVR based on the conventional heat exchanger design and on the self-cleaning design. And this will be made available through our website. So where you just also can make your own calculations to see how designs should look like. And you can even use it to compare designs that you will get from different vendors. So with this slide, I want to end the formal part of this webinar, and we now have time for questions. So we have gotten some questions. So let me select some of them. What if particle entrainment happens? Yeah, so this I guess focuses on the particle separator. We separate based on gravity, which is of course, let's say, the well-known technique. But of course, it's not a 100% proof that no particle can leave. So we have done substantial CFD calculations showing that our design has a very good effectiveness. And even if the flow goes to 175% of the normal flow, still no particle would leave. So we are quite confident that this design is safe. And the benefit of a gravity separator is that it is robust, meaning and there's no sieve then that can get clogged. So that's really a positive. Another question is if it is possible to use this in thin film evaporators. I interpretate this question that and that you talk about a falling film evaporator. We can say that in fact that's not possible because we need a forced flow in opposite direction with the tube fully filled. What we have done is to convert a falling film evaporator into the self-cleaning, but by doing this we also have converted it into a forced circulation evaporator. And in fact we had to change the tube bundle for this, but what we did is we reused the tube. So we took the bundle, removed the shell, cut out the tubes, and then reused the tubes in a new bundle. And we got a very compact arrangement, and this plant is really doing well at the moment. Another question is the lifetime of the particles. Well, the lifetime of the particles is, we know that there will be some weight loss, but this is rather, let's say, limited. So the weight loss will be between 3 and 5% per year. And we know from most recent projects that it's more close to 3% than going up to 5%. At the end, the particle could get too small for a proper operation of the system. So then after 7 to 9 years, you would maybe have a moment that you need to replace the complete batch. But that's, yeah, you can also solve by sieving out the smaller particles. What MOC is to be used for the cleaning particles? Well, that's also a very relevant question. But in fact, we would always look at what material do we need to use for the tubes, for the shell, for the ducts, because that gives an indication from the corrosiveness of the liquid, and that's the determining factor. We would look at that material, and sometimes we choose to go one grade down. So, for example, if all the ducts are from T316, since the particles do have some degradation, you could also use 304 or 302. That's not a big issue. Or you can use 316 particles if all the ducts are from duplex. That will still give you enough particle lifetime. But of course, the more higher grade particle you take, of course, the better the performance in terms of lifetime will be. Yeah, well, the question which is also raised: will the tubes erode and get leak? Well, what we know and what I already said is that from long-term experience, we have seen that there never had to be a tube exchange because it got leaked. We can really fairly say that tube erosion is not a big thing. Another question is, if you have an MVR unit, how would the startup go? This is, of course, this is a very good question, because at the end, if there's no evaporation, the compressor cannot run. So you need something to get everything into the boiling condition. Well, what we would use is, you can use different ways. You can use fresh steam, which of course would give you a faster startup, but you can also use the blower. You then use the same blower, but you run it on air. You generate hot air, and the hot air you then use as heating medium in your evaporator, your heat exchanger bundle, with a recirculating liquid. For the small evaporators, we would also use an electrical heater. So I'm now getting to the end of the questions. Another question is, what is the minimum tube size that can be used? Well, we know that the tube size always has to be quite larger than the particle that we use. So typically we would say with 2 mm particles that we would not go below a tube size of 20 mm in diameter. Okay, yeah, well, that was in fact the end of the questions. So let me see if new questions pop in. No, it's quiet at the moment, so I think we have answered all the questions that are there. So I think we have reached the end of what we wanted to show you today, and hopefully you found it interesting. And if you have any remaining questions, or you want to have a one-on-one conversation, you always can contact us at info@klarenbv.com.